Hello everyone, my name is Kristoffer Carlsson and I will talk about shippable apps and custom sysimages with PackageCompiler. And just to give a little bit of background who I am, I work for Julia Computing, mostly doing various open source projects and tools. And I am involved in developing and maintaining some packages, for example the debugger, one package called OhmyREPL, which is sort of a plugin thing for the Julia REPL, and also PackageCompiler, which I will talk about today. And just to give some context, last year at JuliaCon there was a talk about PackageCompiler, and the summary was basically that it isn't really maintained anymore, and Simon there pretty much asked if someone wanted to take over maintenance. So the PackageCompiler presented here right now is rewritten from scratch actually, and tries to fix some of the problems that occurred with the last version of PackageCompiler. So just to give an outline of the presentation, I will start with describing a little bit about what latency is and what a Julia sysimage is, to give some background. And in the second part I will show how to use PackageCompiler to create sysimage, and then in the end I will also use PackageCompiler to create an app, like something that you can send to someone else and have them run it without having Julia installed. And just a note, the timings in this presentation was done on Julia version 1.4, but in 1.5 and even further in 1.6 there's more improvements, so the timing is going to be lower for some stuff. So let's talk about latency then. So the way we usually define latency here in Julia is sort of the time we spent waiting for useful work to start happening from when we start Julia. So we exclude here, for example, one-time costs we exclude caching from this measurement. And the most common sources are, when you load a package here. So I load plots here, it takes about 6 seconds. And then the second common source is when we actually call functions, we need to compile it and do inference the first time. So here the first time I plot something, it took 12 seconds here, but then the second time it's really fast. So sort of the total latency here, we could measure the time to the first plot, as usually called here, is about 12 seconds from the compilation and 6 seconds from the package loading, which should then be a total of 18 seconds. So the total latency here would be 18 seconds. So what are some strategies then for speeding up package loading? Well, one thing, as I'm sure you all know, is this thing called package precompilation. So the first time you load a package, it does something called a precompilation step, and it takes a bit of time depending on the package. And if we want, we can turn this off using the compiled modules equal no flag, and then we're not going to do this precompilation. And then you see it's a bit faster, but the advantage of using precompilation then is that the next time we load the package, it's significantly faster. So we paid a bit of a one-time cost here to cache some stuff and then have it load faster in the end. And this precompilation cache is tied to a specific version of the package and its dependencies. But like if you use the package manager to update everything, it's going to automatically recompile things. So you don't sort of have to think about this. It's just whenever it needs to, it's going to precompile and make the package load faster. And then what are some strategies for improving the first call latency then? Well, one way to do it is to reduce the optimization level, sort of on a global scale. So it's possible to start Julia with an optimization flag. So here I am putting 0 on the optimization, so we're doing very few optimizations. And then you can see here the time to plot is lower now, it's 6 seconds. If I run with this with the value of 1, it's 8.6 seconds. And if I run with the default 02 here, it's around 12 seconds. So you can see the more we optimize, the longer time things takes, which is kind of expected. And in Julia version 1.5, we can actually set this optimization level not only globally, but also at a module level granularity. And in 1.5, for example, plots will actually use 01 for its plotting function, so it will be a bit faster there. And another way of improving first call latency is to prevent specialization. So specialization is when you compile a function for a specific input argument. So since functions in Julia are generic, for example, f here can take any x, it can be called with many different types, and you can compile the same function for many types. But it's also possible to set something called @noSpecialize here. It's going to compile a generic version that's going to work for many input types. You only have to compile it once, but of course it will be slower at runtime then because it needs to do more dynamic things. And this noSpecialize is not really that much used in normal code. It's hard to know where to put it. It's mostly like inside Julia that's used. Basically, the summary for improving first call latency then is you either compile less or you optimize less. So if we sort of evaluate these latency reduction strategies, we have the package precompilation, and even with that, the package loading can be quite significant. So it took I think it was 8 seconds or something to load, 6 seconds to load plots even with the precompilation. But it's nice, it's sort of automatic and it happens by itself. We don't really need to think about it. Another way is to lower the optimization level or use this noSpecialize, but the problem then is that it can impact runtime, and even with these things the latency can still be quite high. And it's also a bit hard to but the advantage here is that many functions don't really benefit from high optimization levels, so it's fine to lower it. For example, in the case with plots, it's fine to run plots with 0.1, for example. It's going to run just as fast at runtime. And improving all this latency is a high priority. So if we go to the GitHub issue tracker and we look at the issues that have these latency label on them, you can see there's quite many issues open about it, and there's a lot of closed stuff as well. So this is something that's continuously being worked on. But the fact of the matter is, it will likely not be like instantaneous to start Julia and make a plot. Like it's going to be, further down, and in 1.6 it's pretty significantly lower, but it's still not instantaneous. And it probably never will be with this strategy, because compiling things will inevitably take some time. So we can look at the latency of standard libraries then. So Julia comes with a set of these standard libraries. We can look at them here in the Julia repo. We have a bunch of them, like the REPL is a standard library, and we have many of them here. And for example, the package manager is also a standard library, and these load really fast. Like if I measure the time to load the package manager, it takes very short time. So how's that possible, and can't we do the same for our packages? Sort of a reasonable question to ask. And that brings me to the concept of a sysimage. So a sysimage, we can sort of think about that as a Julia session that we have serialized to a file. So where I have installed Julia here on a Mac system, there's this file called sys.dylib, which is 150 megabyte. And we can think of this as that this is like a Julia session that have been saved. And this includes like loaded packages and compiled code. And when we're making the sysimage, all the standard libraries are loaded into it. So here is where Julia creates the sysimage, and it has a bunch of these standard libraries, and somewhere here it loads these standard libraries into the session. And when we just run Julia, like here, we deserialize this sysimage, and that's pretty fast. So deserializing the whole sysimage here is 0.14 seconds on this computer. And I also created a sysimage that didn't have any standard libraries in it, just to see. And then we can see here that when we load PKG, we need to do this precompilation, just like if PKG were any other package. It takes about 7 seconds to precompile the package manager. And then the second time we load PKG, it's faster, but it's nowhere near as fast as it was with the sysimage. But of course, if I don't precompile any standard libraries into the sysimage, you can see it's significantly smaller as well, so we're saving less stuff. So the default, it was about 150 megabytes, and now with no sysimage in it, it's about 55 megabytes. So if we also look at the time to first call for standard libraries, we know they load fast, I showed that, but how about the first call latency? Well, if I use the default sysimage that comes with Julia and I run pkg.status, it's pretty fast. But if I do use the custom sysimage that didn't have the standard libraries, it's pretty slow. So apparently the sysimage also helps with this first call latency problem. So reasonable question is, how does it do that? Well, if we think about how Julia compile methods again, we have generic methods and we compile them for specific argument types. So let's say I have this random function that does something with x here. There's no type requirement here or anything. And we usually when we call this with something like x is a float or something, we compile a specific version of this method. So how can we know what types to compile methods for if we want to sort of save them for the future? Well, one idea is to sort of record what function we compiled for like a representative workload. So for example, we could record all the functions we need when we start Julia and create compiled code for them, save that, and then use those the next time we start Julia, so we don't have to recompile it every time. And this is a little bit similar to this thing called PGO, which is profile guided optimization. And what you do then is you compile a software and then you run a representative workload. You record what stuffs are being compiled, what stuff are being run, and what things are hot, and then you can compile again based on that runtime data. It's a little bit similar about that, but here we're actually choosing what to compile and not what to optimize based on this representative workload. So you can see here that Julia actually, when we compile Julia, we have this representative workload. It starts a REPL and it does some silly things like some printing and timing and so on. And this is just stuff that are very common to use that we don't want to have to recompile every time we restart Julia. And so the REPL has some, and the package manager also has some stuff. It like tries to add a package and so on, just so, and then when that happens, we record all the functions required for that and save the compiled code for that. So there needs to be some way to trace what we compile then. So here I have just an example file that has one generic function that does some simple math, and I call this function with three different types. First with an integer and a float and a matrix. And then I can start Julia in with a specific flag called traceCompile, and I can give this the standard error as an argument, and then I run the file. And if I do that, it's going to print out all the functions it's compiled and for what types it compiled for. So the first time it says here that I'm compiling something for f here with the input type as an integer, so that's this guy then. Then I'm compiling for the same function for a float. And for the third function here, when I give a matrix, it's more things, because when we're calling this with a matrix, more things have to be compiled. So we have to compile matrix multiplication to do this exponential and so on. But in the end, what we compiled was the function f for a matrix of integers then. And we can also redirect all this stuff to a file instead of to the standard error by using by giving something else. Standard error here is a bit special, so if we just give another name, it's going to save it to a file instead. So if I run Julia with this trace compile, the default Julia, it's going to show what it compiles when it starts, and it's like a handful of things that we didn't manage to cache here for various technical reasons. But it's not so many things. Basically everything is already compiled when we start Julia. But if I run this custom sysimage I had that didn't precompile anything, so I have this special sysimage that does not have any of this precompilation in it, then when I start Julia, you see it compiles a lot of methods here, and just continuing, it compiles a lot of stuff. So if we wouldn't have this precompilation system for the sysimage, you would have to compile all this time every time we started Julia, and this would feel kind of slow then. So as a conclusion and a sort of an idea for some kind of tool to help us with this latency is the following observations. Deserializing a sysimage is pretty fast. So if we could give a list of packages to put into like a custom sysimage of us, and we give a representative workload to figure out what types to compile our methods for, then we start Julia with this custom sysimage instead, and we also bundle all these steps into like a nice API, and then we're sort of, we might have some kind of tool that could help us with this latency cost. That is one major thing that PackageCompiler.jl does. So the part 2 then is how to create sysimage with PackageCompiler. So it's pretty simple. The way you do it, you just load a package and then you call create sysimage. Oops. And in there you give a list of the packages that you want to compile. So here I give plots, I say where it should be stored, and then I just tell PackageCompiler to run it, and then I can start Julia with this custom sysimage that I just created. And if we look at the time to load plots, it's pretty much instantaneous, just like a standard library. And actually the time to plotting has also been improved slightly, but it still takes a significant time to do the first plot. So this first step was to show you how to sort of put a package into a custom sysimage to make it fast to load. But if we also want to have this representative workload so that we get the fast first plot as well, we can make a file here that we put our representative workload in. So here I just do really simple one plot call, and then I want to display it, and that's sort of the workload. And the only difference then when I create my new system is I also give this file as the precompile execution file keyword argument. And then it does a sysimage again. So you can see here it takes 184 seconds, while previously it took 150. So it takes a bit longer here because it also has to run this code and generate compiled code for it and so on. But now when I call plot with this sysimage, it's pretty fast. So then you could start Julia and get your first plot in like 0.2 seconds or something, which is pretty good. So if you want to evaluate the benefits of a custom sysimage, we have a fast package load time, and we also have a low first call latency if we provide one of these training script or a representative workload. Some drawbacks to using a custom sysimage is that all dependencies of plots, all the recursive dependencies gets put into the sysimage and they are locked at that version. So basically if you upgrade plots and use the same sysimage as before, it's just going to use the same one. So basically every time you upgrade your packages, you're going to need to recreate this sysimage to sort of get the new versions in there. And it's a bit slower to generate this sysimage. The precompilation step, the normal one, is maybe a minute, while here we could say it took 2.5 minutes for this. And also this is not automatic for you, so you have to explicitly do this yourself. And some good times to use this, if the load time and the first call latency is really long and it sort of makes it be annoying, then it might be worth doing this. And also if you're not frequently changing the packages that you put into the sysimage, then this drawback that you lock the version of the packages is not so bad. So some good packages to put in there could be in the sysimage could be revise, or my REPL works pretty well, the debugger, maybe plots if the time to plot is something that's a bit long. So the third part then is how to create apps with PackageCompiler, and apps are sort of more standalone applications and not libraries. So one way we could run sort of an app is if the app is provided as a Julia package, we can tell someone to install Julia and then use the Git or the package manager to download the package. We have this manifest file that records the version of all dependencies. We can load the package and sort of start the app. And just an example of this, I want to show this redux.jl app, which is does a very simple sort of to-do list made by Knimuk, this guy. So here I'm in the folder of this app. I can start Julia, say to use this project. You can see it's also some dependencies. You can use load the package, and then this is the main function that sort of starts the application. And then we get this window, this GUI. We can say what should be done here. Take out the garbage, buy groceries, and then when we're done it, we can sort of mark them. We can look at what has been done and clear. It's just a very simple GUI. So as an example app. And that's one way to sort of run something that an application in Julia. However, it would be nice if we could just ship an executable without requiring a Julia install. So instead of having to start Julia and use this project and all, we can just like run this thing. So we can think about how Julia itself is shipped. Well, Julia brings the runtime libraries, some other libraries with it. It has a sysimage that we talked about earlier with some precompiled packages. And it has an executable that initializes Julia and starts the repo. That's sort of what Julia is. So one idea for creating an app is that we use a custom sysimage with our own packages and compile code, so we get good latency, just like Julia itself. We bring the Julia runtime libraries with us. Then we have an executable that instead of starting the Julia REPL, it has this custom entry points that sort of start our own app instead. And then we also don't need to bundle any source code since everything is already stored inside the sysimage. So the way you do that in Package Compiler is that you give some kind of source here. So here's this Redux source that I just ran before using Julia, where it should be stored, and also can also give some representative workload. And then Julia is gonna Package Compiler is gonna create a new folder with everything here that's needed to create this app. So it creates a new sysimage with this app in it and all the dependencies. It bundles the Julia libraries, bundles all the artifacts needed. So if you saw, this was a GUI that uses some external library. So the CIM here, it uses some OpenGL libraries and so on. And it's going to bundle those, and then creates an executable that runs this the Julia main function. So if I go back to my terminal here, and then I had run this package compiler here that created this folder. So if we go in there, we can see that we have this bin folder where we have an executable and a sysimage. We have an artifacts folder where we have all the libraries and artifacts used that we need. And we also have a lib folder with the Julia runtime and so on. So now I can just run in the bin folder, and I can just run this thing, and you see it's exactly the same as before, except now we didn't use any local state here. Pretty much we didn't use the local Julia install. Everything is bundled within this file, so it just works exactly the same here. So we could then take this whole directory and sort of ship it to someone else, and they could just run it and without having to install anything. So if we look at the total size here that we're generating, the total size is 290 megabyte in this app, and compressed it's 80 megabyte. So from this around this 290 megabytes, around 95 is this custom sysimage. 65 is actually OpenBLAS, which actually is not used here. We can just delete it, but there's some work to do to make it sort of more automatic to exclude different libraries. LibLLVM comes in at 44 megabyte, and we could potentially drop this with some other flags. And 12 megabyte here is artifacts, just so we sort of know how much space things take. The last thing to discuss is what I call relocatability. So ideally we want to be able to make apps using any Julia package we want. However, to do that, all the dependencies we use need to be relocatable. And the way I define relocatability is we don't embed too many assumptions about the machine that the app will later run on. So just an example is that it's pretty common for packages to embed absolute paths into their source code. And these absolute paths will of course not be valid when you run them somewhere else. So the way this typically happens is that the package defines this build stage that has a build file, and in the build stage it finds a library, and this will return some absolute path to where the library is on this machine, and then it writes this dependency file which says that okay, set this variable to where I found the library. And then when we're running the package for the first time, it's going to precompile, and then it's going to include this dependency file, and then we also define that when the package loads, we're going to open this path that we just defined here. And this runs during the compilation stage. And if we run this on the place where we're actually going to run the package, it's fine. But if we would send the compiled version of this to somewhere else, it wouldn't work anymore, because this path that we find here would be still stored there and would be invalid. And the way to solve this is to use the artifact system. So it's described here in the package manual, how it's used, and it's sort of a declarative way to say what dependencies you use, and a system for loading them that doesn't introduce this problem. So just to make a short evaluation of Julia apps, then, that it's possible to distribute apps made from Julia packages that just runs. For example, the one I showed before, it has binary dependencies and so on, and it still just works. And these apps have a low latency, since we create this custom sysimage and a precompilation script. However, we cannot do any cross-compilation. Julia itself doesn't cross-compile. And the size overhead is a little bit big if we just want to make these small sort of command line apps to distribute them. And it can also be a little bit hard to make a precompiled script or one of these representative workload when we have interactive packages. I have some useful link here that you can, when the presentations gets posted, you can look at them here. Yeah, I think that was all. Thanks, and I think there's some Q&A now.